Here's another video to the lecture Intro PDE. We start with Chapter 2. Chapter 2 is a preparation of the following chapters. In the following chapters we will treat methods to solve the three main examples of second order PDEs, linear PDEs. In fact, we will restrict to second order linear PDEs. These three main examples are Laplace equation, heat equation, and wave equation. Okay, before we do this in chapter 3, 4, and 5, we now introduce some general concepts. These general concepts are at least partially motivated by the first chapter. In the first section, we will prove the divergence theorem. This needs some preparation. Yeah, the divergence theorem. Let me state it. Yeah, that you already know where we want to go. The divergence theorem states the following: the divergence of f integrated over some bounded domain is equal to the integral over the boundary of a product of f with n is orthonormal. Okay. F here is a different f is omega going to Rn differentiable, and omega is a subset in Rn open and bounded. Yeah, this theorem should be considered as the generalization of the fundamental theorem of calculus to higher dimensions. Okay, let's recall this fundamental theorem of calculus. This just states if we integrate a derivative over an interval AB, then this is the difference of the values at the boundary points. Yeah, so we have in this situation omega is an interval. Yeah, so omega is the interval AB, and so an open interval, and the boundary of omega is the boundary of this interval. Yeah, sorry, we used open interval, and this is of course just the finite set of both boundary points. So in this situation, yeah, the boundary consists only of points, and for this reason in this situation this is just an evaluation. But for in higher dimensions, the boundary has some dimension. Yeah, it's not for n larger than 1, d omega is n minus 1 dimensional, and the boundary terms are also integrals. Yeah, for n equals 1, the boundary is 0-dimensional, and this means this is just points, and then we don't need to integral, we just evaluate. So, but this means, yeah, for the statement of the divergence theorem, we need to understand how we have to understand, we have to, maybe I say we have to introduce integrals over submanifolds. Introduce integrals over submanifolds. Okay, so how we do this? Yeah, and this is what we do today. Yeah, so today we just prepare to understand the meaning, of the right-hand side of the divergence theorem. Yeah, we want to understand the right-hand side of the divergence theorem in higher dimensions. So we introduce integration over submanifolds. And before we do this, we first need to understand submanifolds. First, introduce submanifolds. Yeah, if you remember, maybe for those who visit my analysis lecture, they should remember they are related to the implicit function theory. So usually after the implicit function theorem, one also introduces submanifolds. We give here a slightly different definition, but afterwards we will see that this definition is equivalent to the definition which is the usual one related to the implicit function theorem. Yeah, we introduce another one because we will use this other definition later to introduce this new definition 2.1 in order to introduce the integrals over submanifolds. So first we now define subsets, which are subsets of Rn, which have measure 0, so we can't use the Lebesgue integral of Rn to integrate over them. And then later we will introduce a method how to integrate functions on these subsets of measure 0. Okay, so a subset is called a k-dimensional submanifold. If we have here in R2, let's say, example, in R2, one-dimensional submanifold. This is the example which we draw here. This is R, our submanifold. Okay, and this is, so in this situation here, n is 2, okay, and k is 1. We have a homeomorphism, so we have a map 5 for any point x. We have here an open subset, it should be an open subset of A, not of here we have the point x, and now we have an open subset O, which is open in A. This means it is the intersection of an open subset with, it is O is the intersection of an open subset of Rn with A. Okay, so it's a subset of A. And then we have a map phi around any point, and which goes here from some, in our citation, from some interval. U subset of Rk open. For k equal 1, this is at least a union of intervals. So we can restrict to an interval. And now we have this condition. The Jacobian has full rank k. Phi prime, the Jacobian. The Jacobian of phi is clearly an n times k matrix. So if this has rank k, then of course n must be larger than k. Then it can only have rank k then in this situation, larger or equal to k. So this only works for k between 1 and n. So we have 1 smaller equal k, smaller equal to n. And in fact, if k is equal to n, then we know by the inverse function theorem that A is open. For k equal n, A is by the inverse function theorem, because then this is an invertible map. Inverse, if it has rank n, then it's invertible. So A is open in Rn. So then we can use usual Lebesgue measure. We exclude this case. This is not interesting. Because in this situation, because then we use just Lebesgue measure on n to integrate. So this situation, so we are interested in that k is really in between 0 and n. But okay, this is now our situation. Okay, the condition is that on the full domain of definition of phi, the Jacobian should have rank k. And now we want to show, in the following paragraph, we explain that such submanifolds are exactly those subsets of Rn which are by the implicit function theorem level sets, I should say locally, not globally, locally level sets of functions. And now let's say from open subsets of Rn to now to Rn minus k of with derivative, yeah, okay, whose derivatives have rank n minus k. Yeah, so we fix n minus k dimensions and then remain k degrees of freedom. For these reasons, these are k-dimensional submanifolds. Okay, let us explain this. Yeah, also this is, here we describe exactly the situation which enters in the implicit function theorem. Yeah, and then the implicit function theorem tells us that such sets are graphs of the implicitly defined functions. Okay, and this phi, yeah, the phi in the definition, the phi in the definition 2.1 are then the implicitly defined functions by the implicit function theory. Okay, let us see this. Yeah. Okay, if this is an equivalence. Yeah. Okay, let's prove this, or let's argue. Yeah. If the Jacobian, if phi has the properties in this definition, yeah, then choose any point. Then we choose any point in O subset A, and we choose a subspace phi, subspace of Rn, yeah, linear subspace, with the orthogonal projection P phi, such that this map is bijective. Now let's recall from where goes this map. Phi of x with, yeah, this is linear, and it goes from where? It goes from Rk, yeah, yeah, because U is defined, is an open subset of Rk, to phi, and phi is also k-dimensional. Yeah, phi is k-dimensional, so it's a linear map from a k-dimensional vector arm to a k-dimensional vector arm of rank k. Yeah, of rank k. So it is invertible. Yeah, and if this is invertible, then we can apply the inverse function theory. Yeah, okay, now we diminish U and O. So after diminishing U, we obtain a C1 diffeomorphism. Yeah, by the from U to an open subset of V, of the k-dimensional vector space V. Yeah, and a C1 diffeomorphism. Also maybe I draw, let me here give again a picture. We have here this map phi. We have here some point. We have here some interval. Okay, and let's take here the projection which just projects to this interval here. Yeah. P V, so V is just spanned by epsilon. V is just in this situation 0 cross R sitting in R2, yeah, second component. Okay, and then this is here U, and this is an open, and this here is O. Okay, after. Okay, and now this is a diffeomorphism. The composition is a diffeomorphism. Yeah? Composition is diffeomorphism. PV composed with phi is diffeomorphism. Do you all know what a diffeomorphism is? Diffeomorphism means homeomorphism, so a continuous map, bijective, with continuous inverse map, and it's C1, and the inverse map is also C1. Yeah, so it's a homeomorphism. This means a continuous bijective map such that the inverse is also continuous. This means homeomorphism. And diffeomorphism means a homomorphism such which is here in our situation we say C1, maybe C1 diffeomorphism, which is 1 times differentiable such that the inverse is also 1 times differentiable. Okay, and now we can define, yeah, on this open subset which we call here V, times the orthogonal projection, yeah, which is here just the first component. Yeah, so on this strip we can define now a function, and such that this function is just the set A, which sitting here inside. Yeah, and how we define this? We define this function. We identify the Cartesian product as a V cross V prime is of course linear isomorphic to Rn. Yeah, linear isomorphic. Yeah, we can take the map X, Y going to X plus Y. Yeah, this is okay. Here we don't need these brackets. This map, yeah, from V cross orthogonal V perp. Yeah, so orthogonal complement. This is a linear isomorphism, clearly. Yeah, and okay, so we identify. Yeah, we identify this Cartesian product. In this sense, this is an open subset. Yes, so V cross V perp can be considered as open subset of Rn. Yeah, here in our situation, this is just this strip here. Yeah, the strip, the whole strip, the Cartesian product of R cross W. Okay, so and then on this strip, now we define this function here. Yeah, we define this function. We first take Y and set mapping to. Sorry, we should insert here Y. There's missing. I will add this. Yeah, here's missing a Y. So we consider the map which goes to 1 minus PV applied to PV phi inverse of Y. Yeah, also Y sits here in W. Yeah, so Y sits in W. So now we have the composition is a C1, so there exists an inverse map. So we obtain this U. Yeah, and then And then, sorry, I forgot the phi in between. Of course, we need the phi in between. Yeah, we need the phi in between. Okay, so then we apply phi again. Now, so this means we first recover the point here, then we apply phi, and then we use again the decomposition, yeah. And to get the decomposition in y perp, we just use 1 minus pw, yeah. Yeah, 1 minus pw is of course 1 minus pv is of course pv perp, the projection on the orthogonal complement. Okay, so we really get yeah, here and now, so this is a C1 map, this is C1 map, and clearly the zero set of this map, zero set is the part A intersected with W cross V perp. Okay, maybe there exists also in our example here, if some later part may also come here to this strip, so maybe we should restrict also this to a tubular neighborhood. Yeah, okay, but this is not really important. Okay, so this and clearly this map has rank n minus k. Yeah. It can have at most map rank n minus k because the dimension of the image is n minus k, but it has, since independence of set, we have the identity map, yeah, and the dependence of y sits in the rest. So already the partial derivative with respect to 1 is 1. So it clearly has rank n minus k. So, and now this map has rank n minus k. So it fulfills the assumption, the conditions of the implicit function theory. So in this way we see that we are exactly in the situation of the implicit function theory, yeah, and then of course vice versa, yeah, vice versa. The implicit function theorem, shows that phi is implicitly defined by the situation of the implicit function theory. Yeah, which means we have a function of to some n minus k dimensional vector space, which has rank n minus k, to some n minus k dimensional subspace of Rn, which has rank n minus k. And then the level sets are described by graphs of functions. So we are exactly in this situation. And so this implicitly defined function then gives back the map phi. Okay, so this is the first step, and now before we come to the second step, we need some other preparation. So before we can define the integral over submanifolds, we need another concept. Yeah, and this other concept is the partition of unity. Okay, here is the definition. So we have a family of open subsets of the Rn. And the union we just call omega. So omega is covered. We have an arbitrary open covering of omega. And then for this data, we define a smooth partition of unity. This is a countable family of smooth functions with values in the real interval 0, 1 with the following properties. The first property is called local finiteness. Local finiteness. So it means each point has a neighborhood where all but finitely many of these functions, of this sequence of functions, vanish identically on the whole neighborhood. The second point, this is the property which is reflected in the name partition of unity. Here, the sum is 1. Note that due to the first condition, locally, to calculate the sum, we don't need limits, yeah, because of course those functions which vanish we can neglect in the sum, and if only finitely do not vanish on the neighborhood, then on the neighborhood of any point we can restrict the sum to a finite sum, and we don't need to take limits. Yeah? And the third point, this gives the compatibility, in which sense these functions are compatible with the given covering of omega. Each member of this sequence of functions vanishes outside a compact subset of one of this one member of the given open covering. Okay, this is the condition. And this concept, this will allow us, yeah, this concept, will allow us to localize linear expressions. In particular, the integral. The integral is linear, and yeah, because a function, whenever we have a function, yeah, any function f on omega can be decomposed, this is now the essential observation, can be decomposed into f is equal to sum over LHL times f. Yeah, and so we have this members of the partition of unity, multiply this by f, and this this functions HL, f vanish outside a compact set of one member of the given open covering. Yeah, and if we want to do now make some statements about general functions, which is linear, then we can decompose it and now prove the statement. Yeah, Yeah, this is the essential point. So yeah, so linear statements on functions can then be defined and proven locally on one member of the covering. Yeah? Because we decompose this function as a sum of functions which vanish outside a compact subset of one of this open covering. Yeah, okay, and then we just have to, if it's linear, yeah, it's enough to define or prove some statements for this local functions. Yeah, and these local functions vanish outside of one member, outside a compact set of one member of this covering. Okay, now for every family of open subsets there exists a partition of unity. Yeah, a proof you can find in many textbooks, for example in my script on the lecture analysis 2. Yeah, there's given a complete general proof. Okay, now we are ready to define the integral over submanifolds. Yeah, let's look at this definition here. Yeah, now we define the integral over such a submanifold. Okay, we have a k-dimensional submanifold of Rn. And we have a function continuous on A on this submanifold, a real function, which vanishes outside a compact subset K of A. This we assume to guarantee that the integral really is defined and is finite. Now we cover K by finitely many of these open subsets O. By finitely many open subsets O. These are not the same as in definition things, but these maps phi are the same. Okay, let's recall the situation. We have this A. Now we really introduce an open subset O. Yeah? O in Rn open. And we have a map phi as before from some interval u, which goes to A, yeah, which goes to A intersected with O. Yeah, this is the image of this map. Yeah, this the image. Yeah, this is the same as phi of u, and which obeys this condition. Yeah, so this image was in the definition called O, but here O is something different. Okay, we cover K. K is here some compact subset K, and we cover this by such sets O. And since it's compact, yeah, we can cover it by finitely many. Yeah? Since K A is compact, K is covered by finitely many open subsets of open subsets O subset R and N such that O intersecting with I is phi of u of such a map for some map phi as in definition 2.1. Yeah, as in definition 2.1. Okay. Okay, so now we are now we choose corresponding partition of unity. Now, to be more precise, yeah, we have this open subsets O. The union of this open subsets O is some subset omega, and then we choose a partition of unity. Okay, HL. And now we observe again, since K is compact, yeah, and by the local finiteness, every point of K, yeah, for any point of K, there only vanishes on the neighborhood of any point of K, there vanishes only finitely many. Yeah. For any x of K, yeah, by the local finiteness, there exists a neighborhood, or any, for any, or any, now maybe I say any x of K by the local finiteness is contained in an open set, yeah, in an open neighborhood. So is contained in an open neighborhood on which only finitely many H else do not vanish. Yeah. So now we may cover K by this open neighborhoods, and then we see that we need only, since K is compact, we need only finitely many such open neighborhoods to cover K. So it suffices to consider finitely many H else. Okay, so we can assume that our partition of unity only has a finitely many members. Yeah, this follows from the local finiteness and from the compactness of K. Okay, and now we define the integral. Yeah, now we define the integral by this formula. Yeah, by this formula, we take the integral of f over a. This is now the definition. Yeah. We decompose this in this local functions HL, yeah, HLF vanishes each, or any vanishes outside of one of the open subsets O such that O intersecting with A is just the image. Yeah, this is what we assumed. Okay, so now take for any such member, we take the corresponding map phi, O, and U. Yeah? So in this formula, one should consider that the U also depends on L, of course. Yeah? It should be exactly this, the corresponding map phi and the corresponding domain of definition U, such that HLF vanishes outside a compact subset of this. Okay, and then we take this function here. Yeah, so HL composed with phi. Let's draw again our picture. Yeah, we have here our O, subset O. We have here our map phi, and here we have on the interval U. Okay, and then we have the map HLF, yeah, which goes to R. Okay, and the composition here is now a map on U, yeah, with compact support, yeah, because here this is compact. Okay, so yeah, and since phi is a locally a homeomorphism, yeah, it had we assume that it's a homeomorphism, so this is a compact set here, so this has compact support here, and then we take the integral, okay, and take this expression here. Yeah, let's look a little bit at this expression. Yeah, so phi prime, the Jacobian phi prime of x is, of course, it is an n times k matrix. Yeah, and if we take the transposed here, phi prime of x transposed is a k cross n matrix. Yeah, so this product phi prime transposed times phi prime is yeah, so if we multiply the n, these indices are equal, so it's a k by k matrix. So we can take the determinant, and now the claim is it's non-negative since it has full rank. Yeah, also whenever we have a matrix of the form all matrices, yeah, all matrices A. Sorry, maybe we should say what kind of matrices. All n times k matrices A of rank k or for all, yeah, A transposed times A is as a symmetric form, is a symmetrics, is positive definite. And the determinant of A transposed A is larger than 0. So we can take the square root. Yeah. This is easy to see since whenever you have vectors, yeah, then for vectors this is just the scalar product. Yeah, and this expression is the scalar product of the vector with itself, so it's positive. Yeah, so take any vector in the range of this matrix, and then you see this is positive if the vector doesn't vanish. And since the matrix A has rank k, you find linear independent, you find k linear independent vectors. Yeah, this matrix, yeah, is the matrix of all scalar products between the column vectors of A. Yeah, and since this is a k-dimensional space, since A has rank k, yeah, this matrix is positive definite. Yeah, so everything here is well defined. The square root is also well defined. And now we take this integral, take the sum. It's now only a finite sum, and this gives us the definition of our integral. Now, let's look here in this example why we need this factor. Yeah, we just use, of course, here Lebesgue measure d mu. Yeah, Lebesgue measure d mu on Rk. Yeah, this we use to integrate here. And this factor will turn out, this we will see in the next lemma, that this factor is the correct factor which comes from the map phi. Since the map phi changes, of course, yeah, the map phi changes the length scales, so this factor is the correct factor how we should correct the measure on U such that it really describes a measure on this subset A. Yeah, this is the motivation. Okay, and the precise statement is now the following lemma. Yeah, this is now the following lemma. And this is the last statement which we proved today. So, this integral neither depends on the choice of the parametrization by this maps phi, nor on the choice of the partition of unity. So it's really completely independent. Yeah, this is a very general statement. It's completely independent, so it's the natural definition. Of course, this definition looks quite complicated. We first have to take cover k by images of such parametrizations phi, and then we have to choose a partition of unity. Then for any L we have to evaluate this integral, and then we have to take the sum. Okay, so the integral is really complicated defined, but now we see in this lemma that this is the correct way how to do it. Okay, this seems to look like a very general statement, yeah, that it's completely independent of these two choices which we can make, yeah? The choices of the parametrizations of the maps phi and the choices of the partition of unity. And since it's such a general statement, yeah, the proof, one would expect it's a complicated proof. But the proof is astonishing simple. Okay, let's assume we have two such coverings. Let's assume that K is covered by sets of the form phi of U, yeah, and by sets. So we have two such coverings, and the parametrizations of one of these coverings we call phi and the sets U, and the other ones we call psi and the sets we call V. Yeah, we have so we have a family, but since we want to avoid too many indices, we just consider in any case one of these parametrizations in the first set and psi, and denote them by phi and the corresponding parametrizations of the others. So we have a family of such phi. Of course, we already understand they are only finitely many such parametrizations because K is compact, and we also have here finitely many of the psi's. Now take the intersections, yeah, by the intersections phi of u intersecting with psi of v, and now take all combinations, cover also K. So we have now a new covering by the intersections. And for the partition of unities, yeah, the products of the corresponding partitions of unities, so the partition of unities which is compatible here with this open subsets, one partition of unity which is compatible with this open sub, also with the corresponding O's, and a partition of unity which is compatible with the corresponding open subsets here. And now we take pairwise products. Yeah, they form a compatible partition of unity. Yeah, okay, if we take this product, yeah, if we take this product, okay, if sum over L, HL is 1, and sum over H prime K, sum over K is 1, then of course we have the sum over LK, HL times H prime K is also 1 by the distributive law. Yeah? So it's really a partition of unity, and of course HL times HK prime is non-zero only if HL is non-zero and HK prime is non-zero. Yeah, both has to be non-zero. So it's zero outside a compact subset of the intersection of these two. So it's really compatible with this. Yeah. So from two given data, we construct a third one, which is now such that any phi of u is a union of sets phi of u intersecting with psi of v, and also any phi of v is a union of sets of such sets. Okay, so now by considering f, if we multiply f with such a product, also with one member of this new partition of unity, whose members are products, pairwise products of one element of the corresponding partition of unity, which is compatible with the parameterizations phi, and another one which is compatible with the parameterizations psi. Then we obtain sets which vanish outside such a subset. Yeah, so it suffices to prove that for any f with compact support in phi of u intersecting with psi of phi, we have the equality. Yeah, we have that the corresponding contribution by the psi's gives the same as the corresponding contribution by the phi's. Okay, now okay, by restricting, yeah, by restricting phi to, we restrict it to phi from this intersection phi of u intersecting psi of v, and similarly, and we restrict psi to the pre-image of the same subset we may assume that this is just simplification of notation. Yeah? So now we assume that these two images are the same. Yeah? Otherwise, we have to restrict. So what is the situation we are in? Yeah? Let's draw again a picture. Here we have our set A. Now here we have this, on the one side we have this map phi going from some open interval u, and on the other side we have this map psi going from some open interval v. Yeah, both are homeomorphisms. Yeah, so psi and phi are homeomorphisms. So this means, yeah, we may introduce another map. Yeah, we may introduce a map which goes from we call it epsilon, Greek epsilon, yeah, which goes from here to here. This is epsilon. Yeah, epsilon is nothing else but we take psi and compose it with the inverse of phi. Yeah, so there, and then the inverse. And then we clearly have that if we compose phi with epsilon, this is the same as psi. Okay, and phi, epsilon, this goes from V to U. Yeah? V and U are open subsets in Rk. So it makes sense to say that epsilon is differentiable. Now first claim. Epsilon is C1 diffeomorphism. This is now an important step. We will see when we have this, then everything else is just simple calculation. So this is the main thing we have to prove. Okay, how we do this? We choose again such a map V, such that this. Okay. If you look here at this definition, psi is differentiable. So if we can define this as differentiable, then we are done at the inverse. So choose. First. Sorry, this is a local statement. It is enough to prove this at all y in V. Okay, so we have some y in V, and then it's enough to prove this. Okay, then we. Okay, and then of course epsilon of y is in U. Epsilon goes here from here to here, so it's in U. And now choose, as we have done before, choose vector space, vector subspace linear subspace, sorry, choose maybe, choose linear subspace such with orthogonal projection P with orthogonal projection P such that P composed with phi prime of X is invertible. Okay, again, by inverse function theorem, P composed with phi is on an open neighborhood of X, a C1 diffeomorphism to some open subset. Okay. So, but this means then we have that locally psi is equal to phi if and only if P composed with psi is equal to P composed with phi. Okay, and this means that we want to define y is equal to phi composed with ypsilon. This is equivalent to p composed with psi is equal to p composed with phi composed with ypsilon. So now we can write ypsilon. Yeah, ypsilon is of course now the same as pi inverse times this composed. Yeah? P composed with phi inverse is C1 and P composed with psi is C1, so ypsilon is C1. Yeah? This proves the claim. Locally nearby any point. So now this is enough. And now the rest is just a simple calculation and an application of the Jacobi transformation formula. Yeah, we have psi is equal to phi composed with ypsilon. By the chain rule, we have psi prime is of course equal to phi prime. Also phi prime maybe I write by ypsilon of ypsilon composed with ypsilon prime of ypsilon. Yeah, this is the chain rule. So if we insert this, now I don't write always the arguments. Yeah, it should be clear that in phi we should always insert this argument. Okay. And now if we write this, then we obtain that phi psi prime transposed times phi times ypsilon, the whole thing transposed. Yeah, by the chain rule, this is now phi prime times transposed times, and here phi prime times y prime. And here the transposed reverses the order. Yeah, so we get y prime transposed, phi prime transposed, phi prime, y prime. Okay, and we want to take the determinant. Yeah, determinant of this whole thing, phi y prime transposed phi psi prime, then is the determinant of this y prime transposed. This is a k by k matrix, so we can put it out. This is determinant by phi prime transposed phi prime. Here we cannot put it out because these are not matrices. These are n times k matrices. The simple objects are not diagonal matrices from which we can take a determinant, but the last one is determinant y prime. Okay, this is of course the same as so it's determinant of y prime square times determinant of phi prime transposed phi prime. And now if we take the square root, then we obtain here the absolute value. If we take the square root, we get the absolute value here. Okay, and then we just can apply Jacobi transformation formula, and we indeed get this equality. Yeah, so now the theorem follows. Yeah, by now the lemma follows from Jacobi's transformation formula. Okay, this finishes our preparation for the divergence theorem. In the next video we will prove the divergence theorem. Let's recall what we have done today. So we first started with chapter 2. We introduced the divergence theorem, then we defined what we mean by k-dimensional submanifolds. Then we introduced the concept of partition of unity. Then we defined the integral over k-dimensional submanifolds. And then we proved that this integral does not depend on the choices, so is really natural. Thank you.